I'm gonna start taking time. Okay, let's just for the recording quickly because I have to start again now. We are on tangent, right? So it's a line that touches the circle at only one point. If it goes through the circle, right, at multiple points, we call it a secant. Okay, which is never tasted really, but that is the other one. Okay, so the first thing that we should remember from when we did analytical is that a tangent is always perpendicular to a radius. Right? We use that in analytical to find the equation of the tangent. This time around, we're going to use it to work with that 90-degree angle. Okay, because we know in Euclidean geometry, we are actually working with angles all the time, not so much with them. And definitely not with the equations of sides. So guys, the reason here, and I'm just going to say all diameter, this works for with the radius, or diameter, we know that the diameter is basically just an extension of the radius. Okay. So if we have a tangent and a diameter, those two are still perpendicular to each other. The reason for that is just going to be basically what I've written here, but you can just say tan instead of tangent, perpendicular radius, or if it's a diameter, then you have to say tan perpendicular diameter. Okay, so that would be the reason that you would write down if you're using that to calculate. Okay, so that's not really new. It is new in the context of this chapter, but we have seen that before. The second thing, which is the last theorem that we're going to have to prove, is called tan-chord theorem. So that's going to be the reason. Okay, we're not going to do the proof now. We're just going to write it down. So this theorem says an angle, and I'll show you now on pictures, and we're going to practice a whole bunch today. An angle between a tangent and a chord is equal to an angle subtended by the chord in the alternate segment. Sounds super complicated. I will show you on a picture how it works. The reason for this is tan-chord theorem. Okay, so guys, sorry, I'm going to ask you to just draw a circle. We're not going to draw a whole bunch of pictures, we'll just do the one. Draw a circle for me, please. And then when you have your circle, you can draw a tangent to the circle. So it can be any length, right? But just make it kind of go. Remember, tangent has to only touch your circle at one point. Okay? So draw it so that it goes kind of past the circle. Okay, so it's one line like past it. It doesn't have to touch it yet at the one point. Then I want you from that same point where the tangent is touching your circle, so it doesn't have to be absolutely perfect, but you can just draw a chord, right, going from that point to there on the circumference, and then we're kind of drawing like a triangle almost inside the circle. Okay, now guys, if we just read the word thing again, they're saying an angle between a tangent and a chord. Alright, so an angle between a tangent, so we have tangent DE over here. And let's look at chord AC because we have three different chords here, right? AC is a chord, AB is a chord, and then BC is also a chord. Okay. So first I'm looking at tangent DE and chord AC. So we agree that this is the angle that the theorem refers to. Angle between a tangent and a chord. Alright? So that will be angle ACB. We use just a specific color to indicate that angle there. Alright, so the angle between the tangent and the chord. So that includes a little part that's outside the circle, right? If you zoom in here, if I zoom in there, do we see that that angle consists of that little angle there and then an angle in the circle? Okay, so it's not an angle in the circle, it's between a tangent, EE, and the chord AC. Now the theorem says that that angle, right, is equal to the angle subtended by the chord in the alternate segment. So it's equal to the angle subtended by the same chord, right, by AC in the alternate segment, so on the other side of that circle, right? So what angle is being subtended by AC? Angle B, right? So that is what tan chord theorem says. The angle between the tangent and the chord is equal to the angle subtended by that chord on the other side of the chord. Alright, so this angle here between the tangent and the chord, then you look for what angle is subtended by that same chord, angle B. Alright, so tan chord theorem is telling us that these two angles will be equal to each other. Okay, so I'm going to write this next to this picture in blue in the same color. I'm going to say angle ACD is equal to angle B, and the reason for that is going to be tan chord theorem. It is going to take a while for you to be able to recognize that in questions. Because we haven't worked with tangents before, alright, so don't panic. We are going to practice a whole bunch. Okay, so angle ACB, the angle between the tangent and the chord, is equal to the angle that is subtended by that same chord but on the other side. So there's another pair of angles like that. Okay, so now I'm going to take a different color. If we're looking on the other side of that tangent, right? DE. We're looking at the angle between DE and this chord, BC. Right? Then this is the angle that I'm looking at now. If you got different colors, you can just maybe do like two of these things. Okay, like that. You can use a highlighter as well. You can roll a little dot in it. Okay, so tan chord theorem says the angle between the tangent and the chord, right? So this angle here is equal to the angle subtended by the same chord. So now I'm looking at an angle that is subtended by BC, which is what? Angle A. Right? So angle A is going to be equal to that angle. Okay, so for that, I'm going to write what is the name of this outer angle between the tangent and the chord? BCE. Okay, so BCE is going to be equal to the angle subtended by the chord, angle A, and then your reason again is just tan theta. Okay, we are going to do the proof for the theorem, but not today. I just want to practice using it. Alright? But that is then also going to be the last proof. Okay, there's one more theorem that has to do with tangents. It's not one that you have to prove, but you do have to be able to use it. So I'm just going to number this as number 3. Tangents drawn from the same point outside the circle are equal in length. And the reason for that is tans, the short for tangent, from common point. Again, sorry, I'm going to ask you just to draw a very basic picture. So one circle, and then you can just choose any point that's outside the circle. I'm going to draw mine like on the side here, but it's going to wherever, all right? Doesn't matter where that point is. And then from that point, you're going to draw 2 tangents. So just make sure that that tangent touches the circle at only one point. Okay. You can make it go past or you can make it stop at the point of contact. It doesn't matter. Then I'm just going to label that as A, and then this point of contact is going to be B, and that one is going to be C. You can also make a point there if you want. So exactly what the groups are. So guys, what this theorem is saying, right, is that if you have 2 tangents that are both coming from the same point outside the circle, so that would be point A, okay? Then these 2 tangents are going to be equal. But guys, it doesn't refer to the whole tangent, right? It doesn't refer to A all the way to that point, and A all the way to that point over there. it actually only refers to the path of the tangent from that point to the point of contact. Okay, so it's just that section. It's just AB equal to AC. We'll write that on the top. Okay, because that tangent can be drawn for however long they want to go past the point of contact. Because from the point to the point of contact, that will be the same length in both ways. So on the side here, we can say that AB is equal to AC, and then that is your reason. Tans from common point. Guys, how that is actually going to help us, right? Is I want you to draw a chord from B to C. All right, so a straight line going from point B to point C. Right, so we agree that that's a chord. It's going from a point on the circumference to another point on the circumference, right? Now, what type of triangle is that going to be now? Isosceles triangle, okay, which means that this angle will be equal to that angle. Okay, that's actually usually how we use it. We use that theorem to show that that is an isosceles triangle, and then if you have the angle at B, for example, you can say that angle at C is going to be equal to that one. Okay, so that's usually how this theorem is used. So I'm just going to write now that angle ABC will be equal to angle ACB. We are going to practice using it now with some actual numerical examples. And now, what is your reason for that, guys? Why are those two angles equal? What's the reason for isosceles? Angles opposite equal sides, hey? Angles of equal sides. Good guess, though. We would first say that those two sides are equal because the tangents are a common point, and then we would say that the angles would be equal angles. Okay, I'm going to hand out a worksheet now. I'm going to do the first three with you guys, and then you're going to do the rest on your own. And this worksheet is now going to test all of the three tangent things that we were talking about. Sorry, I have to put the double sided. I couldn't get it to like be on one page, and I put it on the next column. But there is a gap on the side. You can stick it in the chat. Research. Right, so number one. They are saying in the heading, study the following figures, determine the values of the letters. Guys, you are going to find them in alphabetical order, right? So for the next one, they do want to find B first and then C. It doesn't really matter in this case, but in other ones, where the one answer kind of leads on from the previous one, you will have to definitely follow alphabetical order. And they say O indicates the center of the circle, all right? So if they're using an O in the question, that is definitely the center. And VA is a tangent. Now, guys, that is something that's a bit strange about this section. In a test, for example, in a question in a textbook, they actually have to tell you that a line is a tangent, right? You can't really just look at a line and say, oh, it looks like a tangent, but only at one point, but it's a tangent. They have to actually tell you that in a question, right? There are also ways of proving that a line is a tangent, which we will do tomorrow. Okay, so we will still get to that. But they're telling us that in all of these questions, BA is a tangent. Okay, so we can use the tangent rules there. Now for this first one, guys, they haven't actually given us any value, but they want us to find the value of A. So does anyone have an idea of what we can do here? BA is a tangent, right? What kind of line is this? They didn't actually label it. Hey, they didn't tell us what that is, but what kind of line is this? A radius, right? And what's that first tangent thing that we wrote down? A tangent is always perpendicular to a radius. Good. So we can use different colors. That is going to be a 90-degree angle. And how does that help you guys? What can I do then? Not necessarily, but
180 minus.
remember what did that tricky angle triangle always add up to? 180. So then I would say 3A plus 2A plus 90 should equal 180. And I also have a triangle, right? And then I can solve for A. All right, so let's write that down. We do need to say here, it's a bit irritating that they didn't label this. Can we just label it, guys? Let's just make it a C. Because we do now actually have to write that that angle is 90 degrees. Okay, so that's going to be our first step. You can write OCA or ACO. It's up to you. It doesn't really matter. Okay, so I'm just going to say ACO is equal to 90 degrees. Your reason is tan perpendicular radius. If you don't have that line, you're going to lose marks. Okay, you have to, everything that's not given, you have to always write that. So then we're going to say 3A plus 2A plus 90 is equal to 180. And your sum the triangle. You can also write that as a shorter way. You can say 5A right from the start if you want to. You can do 180 minus right from the start if you want to. Okay, any kind of, or any line just indicating that you know the three angles on the triangle equal 180. So this is going to give you 5A equal to 90 degrees, right? So we agree with that? So 3A plus 2A is 5A, and then 180 minus 90 is going to give you 90 degrees. This A is 18. Okay, then we're just going to say 90 divided by 5. So the answer for A is 18. Just going to move this up a little bit. Okay, we found that one, guys. So you have to use the tangent rule to get that angle and then just the normal geometry. Okay, I can come inside. Now for the next one. They want us to find B and then they want us to find C. So guys, we're going to have to use tan chord theorem here. Okay, we have a tangent and we have a chord there and a chord there. So again, I'm going to use my two different colors. I'm finding B first. Now guys, I'm going to make B blue. Now B is an angle subtended by this chord, right, on the right hand side. So B is going to be equal to the angle between this chord and the tangent, which is what size? 65 degrees. Okay, so the answer there is going to be A equals 65 degrees. Sorry, B, thank you. B equals 65 and chord theorem. Writing mine over 2 lines because I want to put my answer underneath the picture. And if you want to, if you use blue for that, you can maybe just underline that in blue. So I want to look for on the picture. And then we need to find C as well. Now C is over here, and C is subtended by the chord on the left, okay? Again, they didn't label it, but C is dependent by this chord. So it's going to be equal to the angle between this chord and the tangent, which is 55 degrees, right? So C is going to be 55, same reason, tan chord here. Underline. Okay, fine, guys. If you notice from the start that you're going to use the same reason for both, you could say B equals 65 and C equals 55 tan chord theorem. Okay, if you want to, if you notice that right. Okay, any questions? All right, let's look at number 3. Number 3 is a bit more complicated, right? I mean, already see that we have more stuff going on here. So now they want us to find D and then E and then F. So in that order, D, E, F. But we should notice that we have a point outside the circle, right? Point A. And then we have two tangents going from that same point. So what did we say earlier? Those two tangents are going to be equal in length, making this whole triangle an isosceles triangle, right? So this angle D is going to have the same value as that angle over here. We have the size of the third angle. We have 50 degrees there. So how can I use that to calculate what D is going to be? Minus 50 divided by 2. We use this same method quite often when we have a triangle that's formed by 2 radii, right, inside the circle. Let me quickly show you guys an example. I don't like just speaking and then you don't know what I'm talking about. I think in this first one here. Right, when we did the circle geometry horizons question, right, when we had to find angle F, F2, when we had to find this one, we had that 78, so we say for F2, 180 minus 78 divided by. Okay, same thing that we're going to do here, but now this is an isosceles triangle because of tangents from common points. Okay. But I did just label this again, so I'm not going to first write that this is equal to this. You'll see now I'm going to write my actual calculation. I'm going to say D is equal to 180 minus 50 degrees, that angle there, right? The one that they gave us, over 2. Alright, you have to do 3 reasons for this. Again, just like we did when it was radii, we still need 3 reasons. What's the first one? Angle sum and triangle, right? Because of 180 minus. The second one is angles of equal sides. Because it is an isosceles triangle, that's why we divide it by 2. But then, how do I know that it's an isosceles triangle? They didn't tell us. What's the reason for these two being equal? Tans from common point. So instead of our third reason being radii, like it was before, we now have to say tangents from common point. Okay, and if you work that out, the answer is going to be 65 degrees. And now since we're going to carry on working that, it's again a good idea to actually pull that in on your picture. You're going to have to use that 65 degree angle to get the next answer. Next up, they want us to solve for E. Now you look at E and you see, okay, E is subtended by this chord, right? Do you see that? This chord. Now what do I have around this chord? What angle do I have? Between the tangent and this chord, hey? That's 65 degrees. So when we use tan chord theorem, guys, remember the angle between a tangent and the chord, so the 65, is equal to the angle subtended by that same chord. So E is also going to be 65 degrees. So the tan chord here. Okay, what about X? X is at the center, and we know that the angle at center is 2 times the angle at the circumference. So at the circumference is 65, what's 2 times 65? 130. So X is going to be 130 degrees angle at center equals 2 times angle at center. So that unfortunately you can't just be on the lookout for the tangent theorems. You need to be able to identify any of the ones that you found so far. Okay, so angle at center, angles in same segment can also come up. What else? Opposite angles of cyclic quad, right? If they give you a cyclic quad, you need to be able to look out for that. Just looking at this pictures quickly, and they exterior angle of cyclic quad, yes. In number 19, in number 21, you have a cyclic quad, okay? 21, that's a cyclic quad. So maybe if you have Z, or if you have Y, you can be able to find Z using opposite angles of cyclic quad, possibly. Doesn't look like it comes up anywhere else. Okay. Right, other things that you need to look out for, I'm just looking at number 10, equal chords, equal angles, okay? Do you remember that? Yeah, so X is going to be 26 degrees because of equal chords, equal angles here. In this one, we have an isosceles triangle there, right? They're telling us those two are equal. So those two angles will be equal. You'll have to use that there. In number 12, we have parallel lines, guys. Okay, what happens with parallel lines? Do you see that Z shape there? I do, yeah, ultimate angles. I do want us actually just to label some points here. We might have to, yeah, sorry, let me just go from the start and see where would it be good for us to label points. This one is fine, this one is fine. Yes, this one. In number 7, let's just call that point of contact C there. Can you just call that in on the picture? Yeah. I think that's a 38. Yeah, guys, in number 6, can we make that angle there 38 degrees? This is an unclear there. Then if you're looking at number 8, that's S over there, and that S refers to this whole angle, guys. It does kind of look like it's a circle, but that S there refers to that whole angle. Let's call this one C as well, and then let's call that point D. You might not need it for number 9, but let's just do it just in case. E and C over there. I think these questions are from the textbook from back when you didn't have to have like a reason for each line. So that's why you can just kind of write the answer. For number 10, that one is fine, you don't need anything. 11, let's go in CD. And then the same for 12. Now guys, when I was in the trick, this section, there was not a compulsion, it was a non-compulsory paper 3 that you could decide whether you wanted to sign up for it. And it was stats and geometry and probability, I think, was a paper 3. So I didn't do any of those topics when I was in the because I didn't do paper 3. So yeah, it was like a whole extra. If you look back at like long ago, 2008, 2009, 2010, if you look back at those topics, it's like 1, 2, and but it was like an after school thing. So I remember at my school it was Tuesdays and Thursdays from like 7 to 9. I was like, no way. And I didn't realize you know, and I didn't know I was going to become a maths teacher. So yeah, I had to teach myself all this work when I started teaching and it was back in the syllabus. Okay, so those ones also CDE. So CDE. So this is not on the back of the page, right? 13, 15. We just took the leader. Oh no, what is this here at the bottom? Oh, that's an M. So 16, do we see that that's an M, right? There at the bottom, M. No, how would you get home? Okay, that's fine. We don't need to label anything for 16. For 17, that's an N up there, okay? N, and then there's a P and a Q. 30. Yeah, we're gonna have to label some stuff here. Okay, so let's do that. C. E. P. And we can call that one F word if we really going to use it. Okay, almost there. Sorry. Check so for 16, I didn't label anything, but then for the others, we could check. But we all have the same method. All right, and you can work on that side. There are still 10 minutes left. I'll tell you up until where you must get how it goes, for how long it's going to take to do these.